and he's going to speak about small amplitude water waves in a domain with inclined walls.
Thank you.
Please.
Thank you. And thanks. I'd like to thank the organizers for the whole semester and for the workshop. I am very glad to be here, and I would have liked to stay more, but it's kind of difficult. So this is a work with Rosa Maria Vargas Magaña, and we want to study water waves in a special triangular domain, which I'm going to show here. So the water is between these two rigid walls, and we want to study small oscillations, or oscillations in general. So, the intention of this work was very, should I say, also physical engineering. We wanted to get something out of something that would be a physical result. For example, a question is what happens on the beach. I mean, this is like a model for a beach, and how can you calculate with some model, for example, the height over here of the waves. And so the talk is not is more at the level of finding a model or a reasonable model and see what it can tell you about a question like that, and then the mathematical results might follow. I mean, it's still a question of, first of all, is this model reasonable? Do we get anything that can be measured? So we're still working on these things. The first thing is that we are modeling with a free surface potential flow. So it's an inviscid, incompressible, and constant density fluid that the velocity is given by the gradient of what we call hydrodynamic potential, which is a harmonic function inside the fluid. Yeah, the water is blue, I think, but yes, and the wall, this is the sand. Of course, it's a very simple model, as you can say, because there is no friction, there is no strange effects. But actually, inviscid flow is kind of nice in that the water is supposed to move tangentially, where with viscosity we have more complications. So that's kind of nice for this kind of problem. And now, in fact, there are some exact linear theories. In other words, the study of linear oscillations. In fact, the normal modes are known for a few very special domains that include this 45 domain. That's why I'm choosing this particular domain. It's like a test problem, or and so the question is, if we have that information, at least the linear theory, can we get some kind of nonlinear model? Now, so the story about the 2D, in the case of 2D domains here in 2 dimensions, I think starts with Kirchhoff. He found the normal modes, but there are many other works from the 19th century, and they are mentioned in the book of Lamb. It's a special chapter on that, and there are some more recent results, but not that many. Moreover, there is some extension to 3D channels with constant cross-section and with precisely these special geometries. Actually, the special geometries include the 45 and also a 30-degree domain, which is a little nicer. Perhaps we have a smaller slope, but from looking at these problems from some other, maybe I'll talk about that, some other reason, we realize that maybe this domain is the simplest to work with. So, and as mentioned, that the 3D domains have been studied. Well, some of the work has been reviewed by Groves in a more sort of modern language with some kind of spectral results, etc. So there is some possibility of extending these things now to 3D. Now, of course, we would like to consider more general domains. We cannot say that we can do that, but this is always at the back of our minds, that what kind of generalization we could have. Although I should say that this is a problem where there are many approaches, and in engineering, geophysics, for example, shallow water theory is used nowadays to study this kind of problem. And there is even comparisons with experimental, with observations. There is other, engineers use some packages that have been developed over many decades, perhaps, using even viscous effects and eddy viscosity. So there is a lot of work there. And in fact, it's kind of a sort of question afterwards, where do we fit in all that, if at all? But well, it seems that the potential flow at least has a little bit more capability of modeling a lot of length scales all at once. But I mean, there are difficulties there too. Now, there's also some more specific motivation having to do with the classical works, because the classical works solve this problem, essentially, the eigenvalue problem. It looks like an eigenvalue problem for this normal derivative, which is a normal derivative of the hydrodynamic potential at the free surface of the flat surface, the flat problem, because in the linear problem, everything is flat. And phi is harmonic in the domain, which here is this triangle. And also at the rigid walls, the two walls, we have a vanishing normal velocity. So this just comes from the physical boundary condition. So this is a problem that is solved in these classical works, and people have found these harmonic functions. And we'll get to those, at least for the problem. But when you look at the question of, well, okay, you found those functions, you found the potential, you know the velocities, but how does the shape of the wave look like? That's one of the things you want to know. And usually it says, well, they say, well, it's given by this, which you understand is a result, is coming from the linearized equation for the wave amplitude. But there is something, I mean, and this is taken when you are doing the problem without, with periodic, let's say, boundary conditions. You know that eta is the wave amplitude, and it's a function of some variable x. So you have eta of x and t. So x is here, and eta is the wave amplitude. But then you might ask, in the case of inclined walls, what is the domain of x in this problem? Because the wave is sloshing. So this is not, I don't think this is answered in these classical questions. It just happens that these functions that are found are harmonic in the whole plane and not just this triangle. And so you can extend them, and you can take x to be the whole line, and then you can define the amplitude that's underneath, and then say that, okay, over here, where it crosses, we have where the triple intersection between water, the wall, and air. So, but it's not defined, and perhaps I mean, this is sort of a problem with inclined walls, that somehow we need to think about the domain of x if we want to use such a simple expression for the wave amplitude. And also another problem is where does this, in this theory, what do we linearize to get that? I mean, so this seems to be the linearization from some other geometry that we just put here. So, and if we want to have some non-linear model, we have to start from something that's non-linear and then simplify it. So this is also what we wanted to do here. The other thing that is kind of interesting is that these classical studies give us a certain number of things that are used. We have a fluid domain, which is a triangle. The triangle is actually included in the quarter plane, which is a larger domain. And we have functions that are harmonic in that larger domain, not just a triangle, and have the right boundary conditions. So this kind of device is used, this kind of harmonic functions are used when we study the Stern-Neumann operators, or at least have been used implicitly by many authors. So it's something that we want to use in this problem. And here is actually what we propose. First of all, we have to define what are the dynamical variables, what is evolving. Well, the first thing is the hydrodynamic potential, because that is needed to give us the velocity inside the domain. One novelty here is that we propose to parameterize or describe the free surface by this object, which is the time epsilon map. So for its fixed physical time, you solve an auxiliary ordinary differential equation, and the vector field is the gradient of a harmonic function that has precisely the boundary conditions of the hydrodynamic potential. It's also harmonic. So you solve this ODE and you map the under its time epsilon flow. You map. Let me try this thing. You map this interval to under that flow, and that is what I define to be the surface. So this is the picture over here, now, as I said, V is harmonic. It satisfies Neumann boundary conditions here. So automatically, by this definition, we get area conservation, and that the boundary is invariant under the flow of this auxiliary vector field at its time. And there's some other properties. I think these are the most important ones. Also, we can check it is just by basic local existence theory of OD that also the surface cannot self-intersect and intersects the wall only at the endpoints, that it cannot double. I mean, cannot meet itself, but only it can, and it cannot meet the wall except at the endpoint. So so these are some properties that we are putting in the description of the free surface. One might say, well, it's too much, but it's at least we find it practical. We impose, in other words, a lot of constraints. And then we have some other idea that comes again from the linear theory, that we now are thinking in somewhat more practical way of that the two dynamical quantities that are the hydrodynamic potential and this auxiliary vector field can be expanded in these harmonic functions that come from the linear theory. So we have some kind of expansion, and the goal is to find the evolution of these two quantities, or equivalently to find some equation for the evolution of this coefficient. So these are, again, we are thinking now in terms of some kind of spectral description of the equations, of the dynamical equations. I should say that the free surface, there is something that one might ask, how general a curve do we get this way? This we haven't answered, by the way. There are a lot of asterisks in this work, and I'm going to point some of them, but maybe you can point some of them out, but there might be more than I have thought. But now, one problem is that the definition of the free surface is not explicit. We have to solve at its time a vector field. We can do that, but it's also useful and perhaps necessary to have some explicit approximation of this object in terms of the dynamical variable, this auxiliary vector field. And to do that, we use some approximate solution, some formula for the approximate solution of an ODE, which is used in numerical integration. And I will use quite consistently the simplest possible, which is the Euler formula, the one-step Euler formula. Epsilon, by the way, is a parameter. It's a free parameter of the problem. It's like an amplitude parameter that we introduce. And now the goal is, now, what do we use that for? We use it to obtain evolution equations from the equations of fluid dynamics that I'm going to now discuss. But we can use it for that. In fact, it seems necessary to use an approximate solution, explicit approximate expression of this. And also, we can use it to approximate at its time the free surface. Now, this approximation is not perfect. area is not conserved now automatically, but only to a higher order error. But it has the advantage that if the wall is flat, where the surface is moving, then the image of the surface of the wall is at the wall. So this is appropriate for perhaps piecewise constant boundaries, which is what we want to do at the moment. Now, here are the equations of motion. First, a kinematic condition that the free surface is transported by the flow, and then what Bernoulli's equation, which is Euler's equation for potential flow at the free surface. Now, one thing here is that the dynamical variables, especially this G, appears in the equations implicitly, and it's not clear that we can get anything out of this. Another observation, actually, that we have, that these are two equations because they're two components, and we are going to use only one, only the vertical one, and that would lead to some other equation, actually, which might contradict the first. This is something I cannot consider. I discuss it in what we have written, but I have thought about it a little bit more recently. It's an interesting point, perhaps a limitation or a strength. And then we use some kind of we put the epsilon in front of also of the hydrodynamic potential, and we use the approximate surface to start some kind of, plug into the equations and try to find order by order some equation. Actually, to first order, to lowest order, we recover this wave equation, which is what is solved in the linear by this classical study. So to lowest order, that was encouraging. We recover the problem that was solved before, and we now have all the ingredients. Now, little by little, I will start uncovering what are these potentials. Well, here is again the problem of normal modes. It is useful to define their trace at the flat surface now from -h to h, these 2 points here. I don't know if you can see this blackboard, by the way. And we have actually an orthonormal set. So this is that we use this as a basis at this interval. It is a basis that diagonalizes this operator, and we have also, and now as you go further, I mean, you now look at the work of Kirchhoff, you see that there is some kind of also relation, some equation for the frequencies that is a transcendental equation that you can analyze to great detail. But I should mention now that here comes the sort of one result is that we can go to next order and find and look at the spectral equations using the vertical component of the kinematic equation and Bernoulli's equation and obtain some quadratic system. Here is the linear part, which, as you can see here, is diagonalized, and this is the classical work. Here is the new system. You have mode interactions and some coefficients that depend on integrals of these normal modes, as usual. I mean, in this kind of problems, only more complicated. Now, here is a little bit about these normal modes. Actually, the ground state is something that is just the function x, and it describes a motion that is like that. In fact, the surface is flat, and then you get to the higher modes that have a trigonometric part, oscillatory part, and then you have some part that is exponentially, it grows exponentially, but it grows exponentially. Maybe it's better to say that it's exponentially small in the interior. It concentrates at the boundary. So these two effects appear in the same mode, and then you have some easy asymptotics for the dispersion relation. Here there appears a wave number which comes out of the transcendental equation, but you can see here up to factors that depend on the depth, because the depth is free. These have a very quick, actually, approach to omega equals square root of m, which is the deep water limit. And actually, this is something that I'm showing here, that these are the frequencies up to some scaling. Here is the depth again, the gravity constant. And here is a deep water limit. Here's actually the dispersion relation, a little different from the usual one, which is just the hyperbolic tangent. But these two factors become one very quickly, and we're left with a square root. You see here how quickly, I mean, this already the first, second, third mode are very close to a deep water limit. So this is all from the classical theory, but now the interaction coefficients, this is a difficulty of all this, not very practical. In fact, we are using the fact that looking at the equations and the interaction integrals, that even modes form an invariant subspace, and that is what we're doing at the moment, is looking at even solutions. Unfortunately, these integrals, well, while they can be computed explicitly, the result has to be evaluated numerically, because it's just too long. The formulas are too long, and we had essentially to compute them also by quadrature, just to make sure that we're getting the right answer. So this is actually a difficulty with this method. I mean, the coefficients do not have a simple expression. And one idea was to, perhaps you don't want to calculate the triple integrals of these things, but rather of these things. But that doesn't seem to work. So in the high wavelength limit, it does work, but there's some problems. I mean, I discussed this in some detail, but at least for low modes, it's certainly not going to work. We might end up doing it just for practical reasons. But here is another equivalent form of the equations that I presented you in space form, where I define certain variables, the hydrodynamic potential at the height, at this height, and also the auxiliary potential at the same height. And so I get some kind of PDE here. The intention here was to perhaps try some different discretization in the future. You see here derivatives and this Dirichlet-Neumann operator at the this normal derivative at the free surface. Well, not the free surface, the horizontal line. This thing is completely equivalent to what I have done, because I expanded these functions in the normal modes. And so these boundary conditions are automatically satisfied. But if one wants to see this as a boundary value problem with some initial condition for these functions, there might be some problems. This is a possibility because, and this is one of the difficulties of, I think, of problems with corners. I mean, the solutions, the regularity of solutions cannot be controlled by the boundary data at the corners. I mean, so actually the study of Ming and Wang considers a wedge and considers these questions in more detail. So there's some problems that we don't see here because all operations are done on these functions that are harmonic and smooth everywhere on the plane. Now, this also one idea with this approach is to think that, well, I'm going to work with surface quantities and then define the free surface this way. But then you have the question, okay, if, for example, the normal derivative is not continuous at the boundaries, then you cannot have the quantity, the property that things move along the boundary. So these are some questions about, I mean, if you think what we've done, it can be generalized, but it's not clear that, I mean, there might be some things that we're not taking into account. I mean, you have you need all this construction of these harmonic functions, etc., and smoothness, etc., that may not be available everywhere. I mean, this is an open question. Now, we are looking now at some numerical solutions and basically near monochromatic waves, because I think that's also the simplest thing to try to predict something. We get to see some modulation. We don't go to very high amplitudes. Actually, I'm only doing with two modes, two even modes. This is already, we have a rather complicated ODE. We do see here the amplitude of the modes. You see modulation. We also see these are extended, can be extended to much longer times. We also see possible blow-ups. I mean, there is a real question about the well-posedness of this problem, even in the sense of what is well, this is well posed, but what happens to the solutions? Do they grow without bound? I think some of these questions, well, we're considering some of these questions. Here is a picture of what we get when we look at the surface. And here we see, first of all, that the amplitude is really small. And that's why, even though we have 45 degrees, I have rescaled the vertical axis in a different way. So it looks almost vertical. But we do see some amplitude that is that could be physically relevant. I mean, there's some comments that I made that, I mean, it's not too small, but it's definitely small. And this is precisely to have near monochromatic solutions with some modulation, but higher amplitudes could lead to unbounded growth. So this is something we do not understand at the moment, although in some of these ODEs there are non-trivial fixed points that are unstable and may drive some of these phenomena. They're far from the 1/epsilon from the origin. This is still under investigation and whether that's relevant. We could get some spatial temporal patterns. Perhaps the interesting thing happens over here at the edges, and we can get also, this is what we wanted, the wave amplitude at over here. So what I'm plotting here is precisely the vertical, where does this thing go? I mean, this is the X or Y coordinate of this point and how it oscillates. What we can obtain here is, in addition to some modulation, here, this is a linear problem where epsilon is very small. Then we start to see some modulation, and we also start to see some asymmetry in the minimum and the maximum. Somehow the minimum seems to be bigger. So I think these are some things that one can then try to quantify a little bit just by analyzing these ODEs, even very small truncations, and say, or the frequencies, or and say that these are predictions. But we need to quantify that. But now, one problem also is, well, or one question rather was, for example, the system Hamiltonian. Well, we do not have it's not clear. It doesn't have an obvious Hamiltonian structure. So we did want to look to have a Hamiltonian system. By the way, this is recently appeared here. If one wants to look at details, here is actually a problem with two modes and some kind of more complicated modulation, and perhaps some locking, because this is two modes that in the linear limit it looks more. We seem to have two frequencies now, and the Hamiltonian model actually is for the time being. The result is an equation like that. It's an equation, again, a Hamiltonian in spectral variables and some Hamiltonians, some Hamilton's equations of this form. And I want to describe a little bit that part, and that will be so. So in the Hamiltonian formulation, we want to produce. We actually want to start with a Lagrangian. And we want the Lagrangian to be a functional of the wave amplitude and its time derivative, and then produce via some formal Legendre transformation the Hamiltonian. So, and then we have to also discuss the Dirichlet-Neumann operator which appears in the Hamiltonian. So now here it's useful to have the following analogy. It actually the Hamiltonian is very similar to Zakharov's Hamiltonian, but we're using some geometrical interpretation and connection with Lagrangian by Craig that was later developed in '93, but later developed in some other works, especially more recently, where the Lagrangian actually has for water waves, has a kinetic part which looks like it's quadratic in the velocities and has some position-dependent matrix that's definite, and then some potential energy which is quadratic. So with this structure, which can be also interpreted as a Riemannian metric, I mean, it's supposed to be positive for Q, you obtain by some very standard steps a canonical momentum, which is just this matrix times the velocity, and then you pass to the Hamiltonian, where you have a similar structure, but now it's quadratic in the momenta, and you have here the inverse of this matrix. Now, in Zakharov, this was recognized, at least by Craig, it's described that the Hamiltonian has this form where Xi is the hydrodynamic potential at the free surface. It's operated by the Dirichlet-Neumann operator, and then we have also, and this is the kinetic energy. So the idea was that, well, this is analogous to what I had in the previous picture. If we think of the inverse of the Dirichlet-Neumann operator appearing Neumann Dirichlet under, well, assuming it exists under some condition on eta, and here we have actually derivatives of eta, which is the wave amplitude time derivative. So the idea was that after all, the momentum is given by this object. This is simply the definition of the canonical momentum, and then you get from here to there. So it was guessing the Lagrangian to get the Zakharov Hamiltonian. So and we like to work with the Lagrangian because it indicates that somehow we need to find some description that depends on the time in a quadratic way on the time derivative of whatever describes the free surface. And I have some description of the free surface. Now, so this is so we need to construct a Lagrangian. We have to, it's functional on some configuration variable and its time derivative, and we can choose. We have, this is perhaps the advantage. We have some freedom to choose diffeomorphic choice, at least in finite dimensions. Diffeomorphic choices of the coordinate give me the same Euler-Lagrange equation. So we have a little bit of freedom here because we also don't know what exactly is going to happen. But otherwise, we start with the kinetic and the physical kinetic and potential energy and try to express them in terms of Q of this variable and its derivative. Now, this and this is what we do here. Starting with this, the integral of the velocity square, basically the kinetic energy, we express in the terms of the potential, hydrodynamic potential at the free surface, and here we have a normal derivative. This is defined explicitly. Here we have the surface description. Here's the potential evaluated at the surface. This is explicit, and now here start the approximations. And that's not the only problem, but we approximate here the exact surface by its Euler, the Euler formula, and then finally, which is a function of the auxiliary potential at height b, and And then we reinterpret this definition in this form, that the normal derivative is given by some operator that is known explicitly applied to the derivative, time derivative of this expression. So I'm not giving you this explicitly now. And then also you have some expression for where you have the inverse Dirichlet-Neumann operator. Now, here, and so we basically put all this in the kinetic energy. That's what we do, and obtain some explicit expression of the kinetic energy in terms of these variables, which are basically the auxiliary potential at the free surface. And this expression involves the inverse Dirichlet-Neumann operator that we have to compute as an operator. I mean, we have defined it, but we then apply the sort of machinery, the formal machinery of the Legendre transformation to get the explicit kinetic energy. Well, it's not explicit yet. It involves, this is the canonical momentum, it's explicit. There are some operators that are known explicitly, they have to be approximated, and this is the Dirichlet-Neumann operator that has to be actually computed or approximated. In other words, the Dirichlet-Neumann operator, just as in Zakharov, maps the boundary data to the normal derivative. And here we have an explicit expression in terms of the velocity, but what we need is to see what is this object in terms of the boundary data of the potential. So this needs to be approximated. So in other words, all I'm saying is that after these steps where I produce the Lagrangian, everything else is quite standard. And here's actually where the Lagrangian could not be the physical one. I must say that this is sort of a model. Now, it is interesting, however, that the non-trivial computation is actually this Dirichlet-Neumann operator, and there are several ways to numerically compute it, and we use two of them to actually find an analytic expression. In fact, we're interested in a method. Unfortunately, the title of my page is not appearing, but I will use a method proposed by Ablovic and Haut, where the computation, this was actually proposed for a numerical computation, where you have the potential at the boundary. You specify this is the boundary value. You want to expand it in some linear combination of these harmonic functions that are known at the surface. So here is actually where this method and another set of methods use this equation, these harmonic functions that we have in the problem available. Otherwise, we couldn't have this method, but or we have to produce them. And this is a non-trivial step because we have basically to find the coefficients. We have to. This is a linear operator, basically a linear problem that we have to linear operator we have to invert. And then once we have these coefficients, we simply use the definition and differentiate inside the sum and find and define or have if this can happen, the definition of the normal derivative is just given by this explicit expression. So we this is done numerically, and this was proposed for numerical evaluation, but we have done it perturbatively in a very naive way and found an expression for actually the composition of these two actually linear steps, linear operators. So as you see, again, we have operators that where this is the flat surface Dirichlet-Neumann operator. So this thing always appears in these expansions. I should mention that this, well, how were the coefficients found? What was done? As I said, this is a non-trivial step. It was done simply by observing that the problem is identity plus something, and we invert it in this way. But it's very questionable whether this is completely formal, the derivatives here. So interestingly enough, however, we obtain the same expression using a different approach, which is by Craig and Sulem. They computed this Neumann operator by assuming that it is expanded in other linear operators that are homogeneous in the wave amplitude. And when we do that, we get the same result. So this is kind of interesting, although at the moment it is only to the lowest order, and just to check something that looked very strange. Here, at least there is some theory. At least the problem is considered for constant depth. These are done in a different domain, so it's no theory. Now, I should mention that numerically, of course, this operation is always is kind of complicated, even numerically. I mean, this inversion, and this is and similar problems appear when you go to higher order. So again, but these formulas allow us to get a model, and I think I will finish here actually. And to summarize, we have basically used a definition of the free surface, which is seems to be new. It is complicated. We impose a lot of geometric conditions. We have to relax them somehow to get something where we can get a model. This representation is completely formal. I mean, we don't know how general it is. At least we can get some results and some things that could be considered at least physical results. The question of generalizations to higher domains is not clear. It seems that we can do some of these things with the other domains that I have mentioned, and at least we have this information. Although I think for example, the 30-degree domain, we only know the even mode. So there's still things are, and also there's other problems. One of the domains is a semicircle. Then you have to think a little bit more what is going on there. So we can have, but more generally, there's some questions and perhaps a sort of more involved analytical questions that may be a serious problem. And finally, we have some Lagrangian essentially approach. We postulate a Lagrangian. There's some question about when you simply plug in things in the physical Lagrangian, there might be some constraint where you're not. So the question of how does that compare with the equations is still something we haven't done. But at least we get the Hamiltonian after that with some standard algebraic basically operations, formal operations, and then we also have this Neumann operator, which also is an interesting question in general for this problem, perhaps also in view of the corners. So I think this is it for now. I'm going to finish early, and I apologize for that, but I know nobody's going to complain. So.
Are there any questions?
I can speak louder if you want to.
I think that the online audience can also hear you.
Thanks. Thank you very much. That was a great talk. A couple of things come to mind. So first of all, this idea that you might have blow up in these truncated models. Yeah. There is David Ambrose has some sort of idea that a lot of these quadratically truncated models are ill-posed in this Dirichlet to Neumann general framework.
Yes, yes.
So that's maybe a thing of that. The other thing, I just another couple comments. One thing is resonances. So we don't have if you had a flat bottom 2D without surface tension, there are no triadic resonances in amongst waves. This case, you might have some, right? So
yeah, we don't know.
So that's a
Yes.
a sort of an interesting,
Mhm.
I think, question, which
Yes.
can probably be understood just from the eigenvalue problem, right?
Mhm. Yeah, the eigenvalues, I have estimated the error from the asymptotic precisely to be able to look at these questions.
Right.
But yes, the triple integrals have a different, they're not like the integrals of trigonometry. So we don't know. I don't know. It's an interesting question. Now, about the first question, yes, I think that this is a very serious question. And I mean, I would be somewhat surprised if it's well posed, actually, unless you're talking about very smooth data and for short time. And so, now, what can be done? Perhaps one can be a little practical and consider only small truncations or go to the Hamiltonian model. See, there are questions also because the unstable fixed points, the non-trivial fixed points appear even if you look at one mode solutions. You can get some idea of how close they get to the origin as you increase the wave number. So there can be some things to check. Now, whether now with the high order terms that control things. I mean, I think by looking also at this Lagrangian I put and this, you see that the Dirichlet-Neumann operator is positive definite, but when you make this approximation, you always lose that unless the linearity is very strong. But here it doesn't look strong. In fact, I think that perhaps a weakness of the model is that we use a lot of derivatives because even the wave amplitude has a derivative. So
yeah,
so it is a little bit, you know, iffy in that sense. So
the last question I had is, if you wanted to solve just full Euler in this case, without a truncation, can any conformal map help you?
That I don't know. I think one couldn't. I don't know. But,
I mean, this looks like a conformal mapping problem. Okay.
Yeah, I don't. I mean, to be honest, I don't know that formulation, but I think people have done that, so it could be interesting. I mean.
Okay, let me make a comment after Paul's questions. So because you also about this question about ill-posedness, so Paul mentioned with David Ambrose, and also I think you refer to John Wilkin 2015 paper. So it was also my paper in 2005 with Zakharov that we showed that all such truncation indeed ill-posed, but we basically showed way how to fix it by additional conformal mapping, which is we showed equivalent to some summing of infinite number of divergent diagrams in terms of Feynman perturbation series for Feynman diagrams. So in principle, I mean, we should actually our fault we never tried to implement this 2005 work in any numerics, but my message that there are some ways to kind of right way, I believe, to fix this ill-posedness. Thank you.
Any further questions?
Yes, there could be also the addition of quartic terms, which seems very complicated at the moment. So because also we're in a deep water regime in some sense, so things are, you know. So I think you can think of a lot of things. I'm not, but yeah, thanks. I will look at least at that work. So. And other approaches, perhaps, yes, that is.
Okay, so we are just checking if there are any questions from the online participants.
Okay, no, that's it.
Okay, that doesn't seem to be the case. So let's thank our speaker again. And also let me make a small announcement. I want to, of course, now we have lunch break. We will reconvene as usual at 2:30. And let me also remind you that after the second talk during the afternoon tea, there will be the poster session. And of course, you're all welcome to visit there. Okay, have a nice lunch and see you later.
Well, I will be next week.
Okay.